Okay, we are recording. Can you hear me clearly?
Yes.
Okay, so before let people join, and in the meantime, what I'll do is I'll just quickly recap one thing that is which is also a part of your second assignment, that is trying to find the null space of a find the null space of a vector or a matrix using just elimination. So last time we had discussed how to find the column space and a null space by doing by reducing it to a row reduced echelon form and then taking the independent and the dependent vectors. But we can also do something like this. So last time we discussed this after we had stopped the class, but just for a couple of minutes. So say you have a matrix A, which is m by n, so m rows and n columns. And you are told to find the dimension of the null space and the dimension of the column space of A. So what would you do? So let us take a simpler question, say row space and null space. These two, if I am told to find, what will I do? So if I'm told to find row space and null space of a matrix without doing the row reduced echelon form, can I use elimination to do that? So I will be using an A tilde, that is an augmented matrix. Which will be A, which is m cross n matrix, and I'll also use an identity matrix m cross n. Okay, but I have augmented the A matrix with an identity matrix. But how does that help me is the question. So if you recall, if we do elimination on this, we multiply E, an elimination matrix, with A tilde. What will we get as a result of the product? What should I get?
EA augmented with E.
I don't. You will get E A and E, right?
Yes.
Because E are the, when you multiply any matrix to the left, what it does row operations. So it's an m cross m matrix, which is going to take, it will take the, not n, okay, that's m, the m's, yeah. So it's an m cross m matrix which will act on the rows of the rows of A and try to do what? It will try to make A into this, right? This is how we had done elimination. So this will be how many dimensional? N minus R. Here m minus R, and this will be R dimensional. Yes or no? This will give you the rank. This is how we did elimination. Some matrix you will have on the top, and you will have zeros at the zeros below it, right? Okay. This is row elimination. Okay. So what would I end up having? I will end up having U0, and I am writing E as, say, E, which is, say, R cross M, and E, this is E1 and E2, M minus R cross N. Okay. So I have E1 and E2. Right. So my question here is, what are which is your no row space and which are your null space? Do you recall that? First, tell me, row space is a subspace of.
Um, row space is a subspace of r to the power m. No, r
N.
to the power n. R to the power n.
What is the it's a subspace of r to the power n. What is the call? What is null space a subspace of?
Same. N.
Good.
N.
So what do they form? If you add both of these, they form a direct sum, right? They always add up to r to the power n. You recall we did these things in the first two sessions.
Yes.
So the row space is of dimension r, null space is of dimension m minus r, rather n minus r. Where did I write? Yeah, that is what you get. Now my question is, have I written the things correctly? So let me just check once. M cross n, row space and null space. Yes, that is right. So my question here comes to you, and I'm trying to say to you, what would you be saying about the dimension, or the what are the eigenvectors of the null space? If I ask you, what are the eigenvectors of eigenvectors? What are the basis vectors of a null space? What will you do to the null space? What are the basis vectors? Any? So these belong to r to the power n, right? So u1 will belong to r to the power n, and ur will belong to r to the power n, right? I have just appended a with I. So what do you think E2 is giving me? Simple.
E2. So you appended E with A, and then you appended E2 with A, and you obtained 0. So it is giving the null space, I guess.
Null space. What happened? What is the problem? So these rows, what did it become? What are these
0.
rows? These are zeros. So what does it mean? E2, E2, 1 to E2, M minus R. What will this be? E2, 1 into E into A. What is it? What are the dimension of these vectors? E1, E2, and so on. Hello, am I audible in? Hello, can you hear me?
N dimension. Yes.
They are n dimensions. So E2, 1 into A, what is the value of this? This left hand product. So this row,
Zero.
why is it 0?
Like we are getting a dependent column.
See this A tilde, what is it? It is A comma I, right? Yes or no? This is the
Yes.
augmented, and I multiply one elimination row, that is E21, such that this becomes I into E21, right? This is equal to E21, right?
Yes.
And this becomes E21 into A. And that we have seen is equal to 0, right? In the after we have done elimination. Yes or no? We have seen this. That's how we have constructed this matrix. Yes or no?
Yes.
So where does E21 belong to? It belongs to
Null space.
null space. Null space of A transpose, right? Or the row null space. Ax is equal to 0 is the null space. Xa is equal to 0 is
Yes.
Row null space.
if you're confused, these are all row matrices. Let me write E. These are all row vectors. Because I've written as row vectors here. So if I do elimination, I will get the basis of the null space of A transpose here, and these are basis of what? Row space of A. Right? This is how you will get, this is your assignment question. You can just do elimination and try and just report these two vectors as your
কোনটাকে
row
বললে গো?
space of,
Basis of row
I
space?
don't, how many times will I do the same thing? I don't understand. So this A, you do an elimination, you get U and 0, right?
Yes.
Every time I have to recap from the first class, means you're not studying. That's the thing. So from A, you are doing some row elimination, right? When you're doing the row elimination, you're getting U and 0. What is U?
U is U is that EA and I.
So there's no U. I am just say I am doing row elimination on A, and I get U and 0. So what does it mean? What is the dimension of U? What is the dimension of U? This is simple row reduced echelon form. We did so many times.
Achha.
When we did row reduced echelon, how will I really don't understand what to do. Shouldn't bring up this. Where did we find the null space? Let's check. Here it is. So we did elimination. When you kept on doing elimination, what did you get at the end? You got a series of zeros at the end and U matrix on the top, which had independent and dependent columns, I comma F.
Yes.
Right?
Mm-hmm.
So I should start from the first session laws 001, 001 from every class. Very annoyed. When you do elimination, what happens? You whatever is how many dimension is your null space? In our case, so U.
N minus R.
So this is m dimensional vector. This will become R dimensional. That's what we saw. Isn't it? Number of pivots. You will get I comma F. If you recall this
Yes.
form,
Yes, that will be
this will
R dimension.
R dimension. This will be M minus R. So
Yes.
these would be, this would correspond to the null space of A transpose. We know that there it is M minus R.
Oh, yes.
And we have done row eliminations to obtain these. So which means that the row space has not changed. So these are row space bases.
Acha. Yeah.
We explained so many times that row space eliminate, just doing linear combination of the rows does not change the row space.
Yes.
So when you do elimination intelligently by adding an identity matrix, you automatically get the null space and the. So I said that it will be easier for you to compute in this way, where you will directly get the null space of A transpose here and the row space in the diagonally opposite place. Yes or no?
Yes.
Others, is it okay? I explained this last time at the end of the class, which I did not record. Otherwise, I would not have wasted 20 minutes. Is it okay? Because people see the videos and then they solve the assignments.
Yes.
So the same question which we did by using dependent and independent rows without augmenting, could you complete this? Find the null space and the column space. Can you do that? If I'm told, if I tell you to find column space and null space, what will you do, Oshmit? Column space of A and null space of A. What will you do? Or you have not seen maybe the previous. You can go back and see. Uttrij?
Yes, sir. The last few lectures I missed.
Okay, sure. You can go back and check. Uttrij, what will I do?
Like we will write in that form augmented.
I will augmented matrix. I'll write. Okay, let me write. What will I write? What will I write?
A and I.
If I write A and I, there's a problem. And if I do elimination, I will only get row space and null space of A transpose, isn't it? What does row elimination do? On what is it essentially doing? It's taking the linear combinations of the rows, right?
Yes.
So the rows are how many dimensional? If in A, M cross N. So the column space, what is the dimension of, what is the subspace of column space? It's the subspace of R to the power
M.
So we want these rows to be the basis vectors, yes or no? In this method, because we are going to do elimination, yes or no?
Yes.
So if the rows have to be the basis vectors, what should be the dimension of each of these vectors? If they have to be basis vectors of the column space of A, how many dimensions should they be?
Like they should be M.
M dimensional. So A, just augmenting A will not do. What do I have to do? I have to write A transpose, right? Array null space, row space and null space of A transpose you found. You can just do A transpose. You will find the other two, right? Now is it okay?
Yes.
Now I do the same elimination. This is A tilde transpose. I do another elimination here. Okay. What do I get? Again, something I'll get U tilde 0, E and E2. Yes or no?
Yes.
Now you tell me, do you agree E2 tilde times A tilde or here it is transpose. Yes or no? This is equal to 0. We got this. Exactly, that's what. What does
So
this
null
mean?
space of
I should also write this as transpose to make it simpler for you. So E2 is equal to 0, isn't it? So
Yes.
these rows will belong to the basis of the null space. Yes or no?
Yes.
The same elimination tool you can do and get both of these. You can try to do it in with hand, like pen and paper, and try and do it, and on the same matrix that you have, and see if it matches. Okay, if it is matching, you'll be able to understand what is actually happening. Any questions? I just did not. I wanted to convey this method because it is much simpler method. You don't even need to think about the independent and dependent columns, right? You can just append this matrix and automatically get the results just by doing elimination. Is it still not clear? Any questions you ask, I'll go. Otherwise, I'll go on to like eigenvalues and eigenvectors, because people who didn't do the previous two classes, they can also follow them. Okay, good. So another class of matrices is called the nilpotent matrix. I'll not just go into, there's nothing much details in this. It's just that square, some k power, so of order k is defined as the smallest k such that n to the power k is equal to 0. Okay? In the smallest k such that n to the power k is equal to 0. A very special type of matrices are like truly above the diagonal. If a matrix exists above the diagonal, they will be a nilpotent matrix. Can you tell me why? If any matrix exists above the diagonal, only above the diagonal, anything below it, similarly below the diagonal also, and you multiply itself with it, it will always sometime or the other go to 0. Any idea why? Okay, let's try and see. This is just matrix multiplication and you are keeping quiet. So what can I do? So n is, say, 0, 0, 0. Diagonals are 0. This is 1, 1. What will happen if I multiply n to itself? N squared. What will happen? You are free to choose any of the notation, any of the methods that we learned to do matrix multiplication, either row combination or column combinations. So tell me what will happen. You should be able to tell me in rows or columns, not individual elements. Tell me what will be the first row then. If I ask you what will be the first row.
Like we can multiply 0, 0, 0 with 0, 1, 0.
0, 0, 0 with 0, 1, 0 as in? I understand, but that is just doing element wise. I'm telling, have you again forgotten how to do combination of rows?
So like writing in column vectors, 1, 2, and 3 column vectors will write, and this we will see
Yeah.
as row
So what is
vectors.
this? So then they tell me what is the first column then? If you are writing, if you are comfortable in terms of columns, tell me the first column then.
Like 0 into 0, 1, 0, and 0 into 0, 1, 0 means both three elements will be like
0
that.
into 0, 0, 0, right? 0 into 0, 0, 0, 0 into 0, 1, 0, 0 into 0, 1, 0. What you are saying? I don't know if I
It's,
have not communicated.
I was taking the first matrix as column combination of column vectors.
That's what I am also taking. Is it not? You only told vast matrix of column vectors only I took. And I expanded with respect to this column.
This one only.
So one variable are you getting in the first? In the second one? So if I ask you now, what is the first row? You have told me the column picture, now row. If I tell you write the first row, what will you write?
Linear combination of the rows it will be.
Tell me. I don't know one
Uh,
theory.
0 into 0, 1, 0.
0 into, okay. So it is 0. That doesn't contribute.
Yes.
Next
0
one.
into 1 into 0, 0, 1.
This 1 into this row. Okay.
Yes. 0 into 0, 0, 0.
Then
0 into 0, 0, 0.
so what does it end up being? 0, 0, 1, right? Just this remains.
Yes.
Similarly, for the others, it will become 0. You can check. See the second column. If you multiply the second row, first row becomes 0, second row becomes 0, third one is already 0, right? And you add them. Similarly, the third column is all zeros. Yes or no? So n square is this. What is n cube then? N cube will become all zeros. Can you see that, or do I need to show you that? See this? 0, 0, 0. Why this into 0, 0, 0, 0, 1, 0, 0. Why is this gonna be? What is this gonna be? Everything is 0, the second row and the third row. This is why I told you to use row elimination or column elimination. Which one will only remain? Which is only the non-trivial column? So the first row only has a non-trivial element, right? The second and the third row are all zeros, yes or no? Is it not clear? These two rows, if you're multiplying with the matrix on the right, you take linear combination of the matrix, it's gonna be all 0, right? All the elements of the rows are 0.
Yes.
Yes. Yes. Yes.
So what is the first? When you multiply the first row, what will happen? Only the first, third, corresponding to the third row is 1, which means that also becomes 0. So you're going to get only zeros, right?
Yes.
So anytime you have elements above the diagonal, something like this is guaranteed to go to 0. As even if you have 3, 4, how many ever elements do you have? This will always go to 0, because you see from the last row onwards, you will have an increase in the number of zeros, and this will slowly be shifted upwards and be thrown out of the matrix. So this is an ordered 3 nilpotent matrix. Okay. The last thing about matrices is partition matrices. We have been doing this for a long time, which says that a matrix can be also formed by blocks of other matrices. As you see here, A, B, C, and D can be some block matrices, as we had seen in this case, right? We wrote the matrix in terms of blocks. Yes or no? These are called partition matrices or block matrices. So there's a simple question to ask in block matrices. Show that column space of A plus column space of B is equal to column space of A augmented B. How will I show this? So do you see this M matrix is a block matrix and a some partition with some partition between A and B, right? It's also a partition matrix. A block matrix means the same. Okay. Two blocks A and B being two matrices.
Yes.
What is the only condition of A and B must hold for this to be a block matrix, like a valid matrix M? What is the only condition
The
it must
number
hold?
of rows of B must be equal to that of A.
It should be N cross and M cross B, right? It can be anything, but the number of rows must be equal. Now you are told to say the column space of A plus column space of B is equal to column space of A augmented with B. So how do I show that?
Yes, so
Simple
the
only.
column space of A is AX for all A. The column space of A is
Where say Z belongs to the column space of A plus column space of B. Okay. Z belongs to the
yes
column space of A plus column space of B. So then Z can be written as
AX
what can
plus
it
a
be written as?
BY. AX plus a BY.
What does this mean? O3, how can I change this now? To show that it is equivalent to the column space of A augmented with B, the partition matrix.
Or like we can use the column vector like X
Noted,
and
yes.
Y. Yes, and multiply with
X and Y, right?
Yes, to get that.
Right? This is what you mean. And these two both are vectors. What is the dimension of X? R to the power
R to the
N.
power A.
Sorry, A.
Iota
So
B.
now Z also belongs to column space of A sorted with B. So this is what I have. We do not spend much time on the block matrices because we have been using block matrices directly. Just now I gave you an example of finding the null space using block matrices. Yes or no? So it's the same thing. So when you can do the same multiplication, treat the matrices as numbers, and you can still write the same argument, same row reductions. Is it clear? And then I can go to the last part of linear algebra, that is starting with. That is also another chunk of things, but should be done. I hope it is clear, right? Okay. So what we'll be discussing today is eigenvectors and eigenvalues. So first disclaimer is for square matrices only. And we'll see why just now. Okay, let's see what does this eigenvector and eigenvalue actually mean. Say you have a square matrix. So questions we had asked in the first class, what happens to the column space and null space? All these spaces are the same, right? They all column space, row space, null space and null space of A transpose, all are subspaces of R to the power n. Yes or no? If A is a n cross n vector, n cross n matrix, right? There's no both rows and columns are n dimensional, right?
Yes.
Now I ask you, is there a vector in the column space that does not rotate? Is there a vector a subspace in the column space that does not rotate on operation with A. If I ask you this question, that there is a vector or subspace, whatever you have, that does not have a rotation. And we saw that any multiplication of a vector will all cause some elongation of the vectors and also rotation of the vector, right? These two are the only things that can happen to a vector when you multiply with a matrix, right? You can either elongate it, shrink it, or change the direction of the vector, right? There are only two things associated with a vector. One is the magnitude and is the direction. Yes or no?
Yes.
So I am saying the direction does not change for the vector. So what would you say for those vectors? So what I'm trying to say is, let's just write it. So I have one vector in the column space. This is the column space of A. I have this vector. This is X. Then I multiply this vector with A, right? AX. And the direction does not change. This is what I'm saying. And why am I trying to characterize this type of a special type of a vector? We'll see. We'll see with an example. How is it useful? Is the motivation clear? Geometry of an eigenvector. This is called an eigenvector. Vector of A. This X is called an eigenvector of A. Is the geometry of an eigenvector clear? So I'll because once you get this clear, everything is just calculations.
Yes.
If it is clear, just can we just tell me why? What does it mean? Say A is a matrix n cross n. So how can we formulate this? I have AX and I have X. What would this end up being? Okay, what
Like
will this mean?
it will have same direction with X. That means
Yes.
same X quad means X all the quad column vector, but only magnitude will change. So scaled. So lambda scale.
So you will have some scale Cx, or you generally write as lambda x. Others, it is okay. Is it okay? So when you multiply this with this matrix, it just scales the matrix. It just scales the vector and does not do anything with the direction of the vector, right? Good. So how do we find? So this is called an eigenvalue. And this is extremely essential in machine learning. We'll see it is essential in PCA, something called as a PCA. It is essential in quantum mechanics and many other physics operation or mathematical operations. It makes our life much more easier, these vectors. Why do you tell me how does this make my life easier? And many analytical solutions. So always people will try to find the eigenfunction, eigenvectors, eigenvalues. Why do they want to find it? Because this makes our life simple. And throughout the rest of the class today, we'll see how does it make our life simple. But do you have any broad intuition why does it make our life simple? What, like, how does it even help us? It does not. We don't have to multiply the matrix with a vector, right? We don't need to compute the matrix vector multiplication anymore. We can just use the same x when it is multiplied with the matrix. Yes or no?
Oh yes.
Am I audible? Like I'm not able to hear you. Somebody said oh yes, and then
Yes, yes. You're audible.
so if you don't have any questions, I'll go towards the algebra and calculations and what we can do with it. Okay, you don't have any questions? Good. So how do you think we can calculate this? So there's a simple way, right? If I just write it in this form, do I get a minus lambda I is a of x is equal to 0? I get that this, right? Right, I just took lambda x on the left hand side.
Yes.
Okay, so what does this mean? It means that if x is not equal to 0, then a minus lambda I, what will happen to a minus lambda I then?
It should be 0, means 0 vector.
0, this is a matrix, right? A minus lambda is a matrix or not? A is a matrix. What
No,
did
no,
I
no.
write in the?
Oh, means x is not completely 0. Means identically 0, 0, 0. That is you are telling to.
Yes. If x is not equal to 0, then a minus my lambda I, what should happen to that? What do you understand from this? Is this not familiar?
Or like solution exists and determinant not equals to 0.
Huh? You just your voice just stopped coming.
Yes, the like solution exists. So determinant not
Solution
equals.
exists and all. I don't think there. See, a minus lambda I x is equal to 0. This exists, I'm saying. This means this has a null space. Yes or no? Right, a minus lambda I is equal to b. Bx is equal to 0. What is it? The solution to the null space, yes or no?
Yes, yes, understood.
Solution to null space of a minus lambda I. Is it clear to everybody? But there are two things you need to find. That is both the x and lambda. Both needs to be found. But right, isn't it? Because we don't know what the value of lambda is. How do you find lambda and how do you find x? X I can find if I know b. Yes or no? If b is known, can I find x? I don't know what has happened. If b is
Yes, you
known,
showed the process.
x is just the null space. Solution to null space. Null space. Use any of the two. Use any of two methods we have seen. That is independent plus dependent columns in row reduced echelon form, and number two method is augmented matrix plus elimination. Yes or no?
Yes.
Okay. I'll just take it for granted that you know. If you don't know, please stop me. I'll not ask any questions anymore.
আচ্ছা ওই যে independent
So
plus
how do I find
depend-
lambda now? Huh? What did you say?
ওই independent plus dependent columns in RREF মানে কোনটা বলছো গো?
I don't know what has happened. I have devoted for 100, like one full session doing that, where you asked me how to get the dependent columns and pivots and so on. I don't understand what are you talking about also.
So it is the dimension of null space is n minus r, that one.
You forgot we wrote I and F. We
Oh,
converted
acha.
A to
Minus fi. Yes. Done.
I don't know. But how do I find the values of lambda then? You know this already.
Determinant of a minus lambda I, we will tell it is 0. And by that we'll
That way
find
you have
lambda.
learned, I know. Tell me why is it determinant of A minus lambda is 0? Tell. Why is it 0?
Because since determinant of a minus lambda I into x is equal to 0, and since
A
x
determinant
is not null.
of a vector does not exist. Determinant of vectors
No,
don't make sense.
no, I was saying that a minus lambda I x equal to 0. So x cannot be null. We already said. So a minus lambda I must be 0 then. So determinant of a
A
minus lambda
minus
I.
lambda I must be 0.
No,
This is what I was saying all this while.
the determinant must be 0 then.
Why determinant should be 0? I am saying ax A minus lambda is 0. A minus lambda I into x is 0. This is a matrix, n cross n matrix, and this is a
Rank is less than n, that is why.
A minus lambda I has the dimension of this is n minus rank. N minus dimension of null space of A
Oh,
minus
rank
lambda I.
to full rank. Oh, আচ্ছা বুঝতে পেরেছি।
This is the rank. Dimension of A minus I is equal to the rank of the matrix is equal to rank nullity theorem, which we proved. It is n minus the dimension of the null space of A minus A minus lambda I, which is greater
Yes,
than
yes,
0.
that one is clear.
And this is less than n then, which means
This is less
there
than.
is,
Oh,
so this is a singular matrix.
yes, yes. Since it is not
So
full rank.
So A minus lambda, if I write it in terms of a determinant, I can at the end of the day get a row at the end which is 0, all zeros. And I can do the same operations in a determinant that I can do in a row elimination, right? And it does not
Yes.
change the determinant value, class 11, 12, I will not. And I'll get zeros at the end, which means the determinant has to be 0. And you're saying A minus lambda is 0. This is called a singular matrix. Good. So this will give me determinant of A minus lambda I is equal to 0. So from here we get something that is called as a characteristics polynomial. So now we found two ways. First, we have to find the values of lambda, and then once we know the value of lambda, A minus lambda I is eigenvectors, right? That is equivalent to finding the null space of A minus lambda I. Clear? If it is not, let us see in this question. Say you have a, so this is defined as a PA of t is equal to determinant of ti minus a is defined as a characteristic polynomial. Characteristic polynomial of matrix A. Why is it called a characteristic polynomial? Because it gives us a lot of characteristics about the matrix. What characteristics we'll see just now? It gives us the values of the eigenvalues, the eigenvectors, the null space, idea about the null space. It gives us the number of the dimensionality of the row space and the column spaces of a minus lambda I. All of these we will get from this equation with the help of starting from this equation. Okay, I have just written a minus lambda I as I have replaced that lambda as t and written this. This is like t is easier to write. That's why. This is okay, and I've written t in the beginning. It's cumbersome to deal with t's at the end, minus t's. So I've written ti minus a. I don't think there's any issue if I write ti minus a and a minus ti, both the same determinants. Yes or no? Okay, good. I'll not ask more than once. T minus, so I am telling you to find a characteristic polynomial of this matrix A, right? What will you do? Determinant of what is P A of T? Determinant of I have a matrix A given to me, A, B, C, D. Are you following?
Okay, like it will be T minus A, B, C, and T minus D.
Huh?
Like you are doing Ti minus A, so in the diagonal elements, we will have T minus A and T minus D and B and C.
I hope this is clear to everyone. It's not yet appeared on the screen. Okay. Okay, where is it happening? So what does this, what will this give me? TA, T minus D minus BC, which is T square minus A plus D into T plus AD minus BC, right? Right?
Yes.
So what are the roots of, so do you agree the roots of T are the eigenvalues we need? Yes or no? Do you agree?
Yes.
Because instead of lambda, I have just written T. So roots of lambda is same as roots of T. So can I get some information from this equation about the roots? See this A plus D. A plus D is equal to lambda 1 plus lambda 2. Yes or no? Okay, they are lambda 1 comma lambda 2, the roots of a quadratic equation. The sum of the roots is equal to the coefficient
Trace.
of, yeah, that is true, but just from the polynomial science points of view, the sum of the roots is equal to the coefficient of the term n minus 1th term. Yes or no? If
Yes.
or degree n polynomial, the n minus 1th term coefficient would be the sum of the roots. Similarly, the product of the roots would be AD minus BC. Yes or no?
Yes. Determinant.
This is equal to nothing but, you see, determinant of A is equal to AD minus BC. This is determinant of A. And this is nothing but the trace of, this is nothing but the trace of A. So we can easily find two things from a matrix, given a matrix, the product of the roots and the sum of the roots, right? Sum of the roots, that is the sum of eigenvalues is equal to trace. The product of the eigenvalues is equal to determinant. Last time we had also shown this for a n by n matrix. How can we show it from a n by n matrix? Any idea? If there are, it's an n by n matrix, how many roots would you have?
We would have n roots.
Determinant of t11, t a22, t minus nn, right? And you will have some matrix here A, some sub diagonal A12 dot 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 A1n, AN1. So this determinant you will have to find clearly, that will have, it's a order t to the power n summation of aii t to the power n minus 1, and you will have a lot of insignificant terms. At the end you will have determinant of A, and you can show this by induction. You can show for a n by n matrix and then show it for n by 1 cross n by n plus 1 cross n plus 1 matrix. It's just simple things. Like 2 to 3 you can show. You can use the determinants of 2, right? We can use a smaller determinant to find a larger determinant. Yes or no? If you have to find a determinant of n plus 1 by n plus 1 matrix, you can use a n by n matrix. Yes or no? To determinant of n by n matrix.
Yes.
So it's exactly similarly, you can just do that and show that it is true for a for any case. So let's use this. So, and let's also use a similar thing first, like how can we also, so from your factorization 11 12 factorization, not 5 7 8 factorization, from 11 12 factorization, what can I write this equation as? Can you tell me? Can I like say any polynomial t to the power n plus t to the power, so this is your an, so you have t to the power n, and then you have an minus 1, or let me just write a1 t to the power n minus 1 plus a2 to the power n minus 2 dot 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 an, right? If I have this polynomial p of t, what can I write this as? Necessarily you need not be telling me the answer in terms of A's given here. You can give me any generic answer. An order
Like
n polynomial. Yeah.
means what we have to do, we have to factorize into roots.
Yes. Yes. Exactly. So this I can write as alpha 1 t minus alpha 2 dot 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 t minus alpha n, right?
Oh, acha, means the relation of roots and coefficients. So
Relation of roots and coefficient, but you like always you need not, so you, these two forms are equivalent. You will have some correlation, of course, product of 2, product of 3, yes, you're right. But I'm just saying you would always be able to, there's a unique factorization to a polynomial, yes or no? We know that. This is
yes.
useful then. So generally you have, so these are called your eigenvalues, right? These roots are your eigenvalues, yes or no? They are solution to your a minus lambda is determinants. So these are your eigenvalues, yes or no? Okay.
Yes. Yes.
Now you can also have repeated eigenvalues. I will show you one example. Say what is the eigenvalue of the identity matrix? Do you also agree that this way what is there to show also? So this is nothing but t minus 1 whole cube equal to 0, right? The determinant of, so if I write an I3, what is determinant of ti minus I3? What is the determinant?
Oh, t minus 1 whole cube.
T minus 1 whole cube equal to 0. So T has 3, 1, 1, 1 repeated eigenvalues. Yes or no? So you all know that, right? So any polynomial T can be always written as a product of T minus alpha i's, I equal to, say it has k roots, k distinct roots, and each has a power of ni, such that ni, summation of ni will be equal to n. Yes or no?
Yes.
Is this method clear? Is this? I hope this is clear, right? Any polynomial can be written in this form. Just a revision from your class 11 and 12. Your roots ni can be ni is greater than or equal to 1, and of course less than or equal to n. Okay. And k is the number of distinct roots that you have. So here you have only one distinct root. So the idea is, so you can have lower number of, so at most how many distinct eigenvalues will you have? Eigenvectors will you have? Eigenvalues will you have? Question. At most how many distinct eigenvalues? They ask you, what is the answer?
1, we can have 1 repeated many times.
No, I'm at most how many distinct eigenvalues will you have? Distinct.
Okay, yeah. Acha, n.
N for a n by n matrix. Minimum is 1, right? Agreed? Like we saw for I3. This is the maximum, this is the minimum. Okay. Now let's do the question that we had left from last time. Very interesting question. Where is it? Huh. Where? Show that trace of an idempotent matrix is equal to rank of the matrix. How will I show it? Trace of an idempotent matrix is equal to the rank of the matrix. Any idea? Let's do it at the end. Trace of idempotent say A is, say, a p squared. What is the definition of idempotent matrix? If you recall from last time. What is the definition of an idempotent matrix?
Means like this will give the value of p again.
P square is equal to P, right? Projection matrix was an example where the same matrix was obtained in the one multiplying itself. Yes or no?
Yes.
So now if I'm telling you, say trace of P is equal to rank of P. How can you prove this? And how can you use methods of teaching to answer this question? Like simply. What process should I use? Like what tools should I use to solve this? Just now I taught you the tool, so I'll be, of course, using that tool. Yes or no? Should think in that terms. What did I teach you just now? What did I teach?
Like writing the characteristic polynomial.
Other than that, what was the topic, broad topic that I was teaching?
Eigenvectors and eigenvalues.
So and I have used trace there, yes or no? So like this, you should be connecting. This should give you the intuition. Have I not used trace there? What is trace?
Trace is the sum of roots.
Sum of eigenvalues.
Eigenvalues.
Sum of all the eigenvalues is equal to the trace. Now I have to find the eigenvalues. That's it. So what can I do? Px is equal to lambda x. Yes or no? As soon as I see trace, it should click that it should be an eigenvalue sort of a thing. Is it okay?
Yes.
So now this is the eigenvalue, eigen equation. Okay. Now my question is, how can I use so I have used the eigen equations. What is the other condition that is given to me to solve this question? How do you think I'm trying to explain to you? I have used the eigen equation from the trace. Other condition is given is the other condition that is given. What is the special type of matrix that is given to us?
The
P square equal to P is
equals to,
given.
yes, we can multiply P.
Why are you not following? I'm going so slow. What is the issue? Others, please follow. And even if you have not attended previous classes, this is independent material now. So P squared x is equal to lambda px. Yes or no?
Yes.
What is P square?
Again P.
So Px is equal to, and Px is from previous Px. What is Px value?
Lambda x.
So lambda square x. So Px is also equal to lambda x left hand side. Yes or no? This is from idempotent. This is from eigenpair. Yes or no?
Yes.
Agreed? So do you agree? Lambda into lambda minus 1 is equal to 0 as x is not equal to 0. Right? That is lambda is 0 or 1. Correct?
Yes.
Correct. Now we'll see is if it is 0 or 1. How many? So the question is, how can you? Yeah.
এখান থেকে মানে basically I can say that if all are ones, then trace will be equal to its number of columns. But even if there is 1 0, its determinant will be 0, which means rank is smaller than n. So, and if all are ones, then it will be equal to n. So, and the determinant is 1. Therefore, rank is also n. So, rank and
Yes.
this becomes equal. In that way.
No. So lambdas are either 0 or 1 is what I am claiming. I have proved, right?
Acha.
So corresponding to all of these zeros are the null space vectors. Yes or no?
Ax equal to 0. ঠিক.
Ax is equal to 0. These are all null space dims. So if you have dimension of, say, null space of A is equal to dimension of null space of A is equal to k, then you will have k zeros at least. Yes or no?
Yes.
You have to have k0 vectors automatically from the dimensionality of from the determinant property. So you will how many how many ones will you have? Number of ones is equal to number of
n minus k.
dimension of the column space of A is equal to rank is equal to n minus k. This is also equal to the rank of A. So do you see the trace is equal to the rank? Clear? Any questions?
Yes.
Okay. If this is clear, let's go and see something called as, I'll tell you a few definitions. Before that, let's see. Yeah. So these NIs, okay, these NIs, NI is called, what do you know what is this NI is called? These are called, these NIs are called the algebraic multiplicity of the eigenvalue. Why is it called the algebraic multiplicity? Because it's the number of repetitions, right, of the root. That's what you call the multiplicity of a root, right? What is multiplicity of a root? It is the number of times the root repeats itself. Yes or no?
Yes.
So number of times the root repeats itself will be the algebraic multiplicity of the eigenvalue, and the geometric multiplicity of, and we have another multiplicity, we'll see that it is called geometric multiplicity. This is the dimension of null space of A minus lambda I, or in our case alpha I. Okay, so this is the geometric multiplicity of alpha I. So that what is the dimension of the null space? We'll see they need not always be equal. I'll show you what is the case, and then I'll come to this last few questions, that is similarity transformations and so on. And just a point to remember, just before I go into, so you see, right? So PA of T is determinant of PI minus A, right? So you can intuitively think PA of A is determinant of T into T, can be, you can put A. This is 0, right? Intuitively, this is not true. This step is not correct. Not correct step. Okay, but do you see that if you put the value of A in the determinant, you should get 0, right?
Yes.
Yeah. But can you tell me why is it not correct? Like, so remember this fact. This is a fact, and the way to remember is just putting the value of A in this equation. But this is not a correct step. It just coincidentally holds true. PA of A is equal to,
T is a value, means how can we put a
exactly,
matrix there?
exactly. This is a scalar. Scalar. So for to show that, we would need what is called a so to show that the actual proof is something like this. It is done like very clearly in the last course. I'll not do it this time. It's not, if you are appearing for Gate, please go back and see that. It's very useful. That's called Cauchy's triangularization. We're not going into that this time. But the idea is, can I write PA of T as T minus alpha 1, T minus alpha 2? Here I'm just considering repetition as also. Dot 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 T minus alpha n. I can write this. Yes or no? Yes.
Yes.
Any questions? Now can I put the values of A somehow? Now I can put. Can you tell me why? Because I can write in place of T a matrix and also write alpha 1 I. right? We can any equation can be written as a matrix equation by just when you subtract a scalar by multiplying an identity. Yes or no? I hope that is. So this is the actual step. A minus alpha ni. So there is I'll not keep you in the dark. There is a type of, we have seen A equal to LU decomposition, right? There is also a type of decomposition called a Schur's triangularization decomposition, which you can write this as U transpose. Its Hermitian is nothing but transpose. I'll come to it. Think of it as transpose now. Transpose for the time being. It is a triangular matrix and a U matrix, where U Hermitian U is equal to I. This is called a unitary matrix. Okay, so in this case, this triangular matrix T11, T22, dot 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 Tnn, and you have some elements on the top, and this is 0. These correspond to the eigenvalues. These are alpha 1, alpha 2, dot 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 alpha n. Now, if you just try and multiply, now do you see why it will be true? Can you tell me? I'm not showing. This is called Schur's triangularization. I am not going to show you this thing, but I'll show you the proof given that is true. I have shown Schur's triangularization in the previous course. You can just go back and see. Okay, can you help me how to do this? If A can be written as U Hermitian, a triangle matrix into U, how can I write PA of A as? How can I write it? Hello, am I audible?
What is the next element of U Hermitian details told?
U Hermitian, a triangular matrix, and a U. Another. These are the okay. Since you have asked, these are unitary matrices. Unitary matrices are equivalent to. Can you tell me what will it be equivalent to? We have already learned it in the previous class. From this equation, you should be able to tell me. We learned, right? Q transpose Q equal to I. You recall?
Orthogonal matrices.
Orthonormal matrices. So unitary matrices are a superset of orthonormal matrices. Can you tell me why?
Because transpose stands for only real matrices, but the
Good.
Hermitian stands for complex as well.
So what is U Hermitian? People who do not know, I think you should know this. It was there in your 11 and 12, but in case you have not paid attention, so U11, U12, dot 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 U1n, UN1, dot 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 UN n. So if U is a what type of a matrix? A complex matrix. Okay, it's very useful in Fourier analysis. You may study that when you're doing Fourier transforms and so on. So say U is a complex matrix, right? So in that case, your equivalent transform is not U transpose, rather U Hermitian is helpful. Can you tell me why is U Hermitian helpful? So U Hermitian Ij is defined as Uji conjugate, right? If I give an example, U is equal to A plus IB, C plus ID, E plus IF, and G plus IH. What is U Hermitian then? What is U Hermitian then? You'll take the transpose and make the conjugate. Two things you have to do.
Like G minus IH.
A minus IB, you mean? A minus IB, P minus ID, E minus IF, and G minus IH. Yes, this or not? This is what you mean?
But Dada, you wrote GI, so means won't we
U
take the
Hermitian means transpose conjugate. U Hermitian means transpose conjugate. Right?
oh acha, okay.
No, what was this? So U Hermitian I defined IJ as JI, right? So for the time being, forget about these matrices. Just think that U transpose U is equal to I. And I'll show you. You have to use complex matrices in eigenvalues and eigenvectors because roots can always be complex. So you can't do anything. So this is the only place you'll be using complex matrices, not anywhere else in general UG courses. Okay, so what I can write as PA of A as? I can write this as U. Can I write it this way? Can I write this?
Yes.
Why? This
Like
is
that
I already
UHU
yeah.
is I again. UHU
Well,
is I again.
yes. This is again I. And this is nothing but A, as we have seen from the Schur's triangularization definition. Now what will I do? Simple only. I equal to 1 to n. I'll take U Hermitian out. Triangle minus alpha I, right? Into U. Is this right? Correct?
Yes.
Now you see, if I multiply this, what will I get? If I multiply all of these elements, just put it somewhere here. So all the ith element would, yeah, well,
A minus lambda I.
A minus lambda I থেকে I wrote into this. I want to put this back into these equations. A minus lambda I can be written as U Hermitian triangle matrix minus lambda alpha I into U. Each of these
ও
components. Yes or
আচ্ছা,
no?
এটা হবে U Hermitian into that triangle minus AI whole to the power something n একটা হবে।
Whole to the
হ্যাঁ
product.
হ্যাঁ 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 হ্যাঁ
Whole to
প্রোডাক্ট
the
প্রোডাক্ট কারণ ও সেম নয়।
alpha is are different. Yeah. So this is clear to everybody. So because you will each of them will have a this term will have a U here and this term will have a U Hermitian here. Yes or no?
Oh yes,
This
yes, yes.
this will have a U here. This will have a U Hermitian here. This will have a U here. This will have a U Hermitian here. All of these will be paired up into I. Now you see, for each of this element, one of the diagonals will be 0, right? Yes or no? So lambda, what is the value of the triangle matrix? It is alpha 1, alpha 2, dot, 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 alpha n. And you have some star, yes or no? On the top and zeros on the denominator. This can be asked. That's why I'm trying to just show this. Is this clear? This
Oh
is what we
yes, yes.
define.
Then
Now
okay.
if I, good. So if I multiply, if I say this is the first term, term 1, what will I get? I'll get 1, 0, alpha 2 minus alpha 1, alpha 3 minus alpha 1, dot, 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 alpha n minus alpha 1, right? Some star and zeros, yes or no?
Yes.
Similarly, term I will be.
Why are you saying the stars? Mane mane are there
They can be anything.
non-zero elements in that stars?
So I have said it's an upper triangular matrix. What does it mean?
Oh, আচ্ছা ওটা upper triangular. আচ্ছা ঠিক আছে।
Yes, it's an upper triangular matrix. So the next element will be alpha 1 minus alpha 2, 0. And then you will have all these stars. Next element will be alpha 1 minus alpha 3, alpha 2 minus alpha 3, 0, and then all these elements. Yes or no?
Yes.
এই করে multiply করলে এটা 0 আসে। Just do it row wise and see. So this first column is all zeros. Again, this is all zeros. So you will end up having all zeros in the first row, second row, third row, and so on. This guarantees, this two product will guarantee first two rows being 0 and so on. You can just try it as your homework and you'll be able to see that they are. I'll just do it for the first two multiplications and then it will be very simple for you. Tell me what would be the value of the first element in this? Do you agree it will be 0? Like the first 1 element. If I multiply T1 and T2, is it okay? Yes or no?
Yes, 0.
It is 0 because you have a lot of, this is 0 and you have a lot of star elements over here, but these are all zeros. Correct? Similarly, what would be the value of your? Now what are we? This is 0 we have already got. Similarly, second row, what is going to be the value? The second row, this is already 0. Right? So, and then you will have these elements. Where is it? Some element star will be here. It's going to be 0. Yes or no? Let's just show you these elements. Just give me. So just multiply T1 and T2. Okay. So what is the value of Tij? So T1 into T2 ijth element. How can I write this as? Is a summation. This matrix into this matrix, the element, the product of the two matrices, the ijth element. How can I write? T1 ik into T2 kj summation of k equal to
Summation
0 to
k
n.
equals to
So the
k
ith
equals to
row
1 to n হবে না? K equals to
yes,
1
1
to
to
n.
n. All these things are like trivial. So the ith row and the jth column. Yes or no? Right? Do you agree?
Yes.
So now tell me, ith row and the jth column, if the values of, if j is greater than, what is the value? So j is greater than, for all this value, for k greater than j, what will happen? For k greater than j, and for I less than, k less than I, what will happen? K less than I or k greater than j, what will happen? Do you see the product going to 0?
আচ্ছা, yes.
So these two will be T1 ik is equal to 0 if k is less than I. Yes or no? These values below the diagonal. Similarly, T2 jk or kj is equal to 0 for k greater than j, yes or no? So only you are left with which terms? Between I and j, right? Is it okay? This is equal to summation of k equal to I to j, yes or no? I don't know what is the issue. Okay, I'll not go into details then. Is this clear or not clear? What is the problem? These two terms are zero, yes or no? Let me draw a matrix and it will be clear. See the visualization. We have a diagonal and we have elements on the top, which is star. You take the ith row. What is the diagonal element position? I comma I, yes or no?
Yes.
Diagonal and anything to the right is not zero, greater than zero or not equal to zero, right?
Yes.
These are all zero, yes or no?
Yes.
This is all zero. Similarly, if you have a j somewhere here, this is j. Everything from here, this is not zero, but everything below it is zero, right?
Yes.
Now that's what I wrote. So what did I write? I wrote the t I k for k less than I. So this is this case. And this is this case, right?
Acha, understood. Yes.
So all those terms goes to zero. Only between I and j will it be any other term. So for 1, 2, for your matrices which is a 1, 2. So if your I is 1 and j is 1, what will you get? If I equal to j equal to 1, what will you get? You will get t1 1 1 into t2 1 1, yes or no? So you will get this element as 0, the first element of the column. है कि ना? What can I do now? Is it clear or not? You can just see and multiply. I don't know how to explain. Which is
yes,
which
0.
this first element t11 is 0. Already I have seen. They have shown this is 0 because it's alpha 1 minus alpha 1. Similarly, if I and j is equal to I equal to j equal to 2, then so you will have t2 2 comma 2 is 0. So this column also becomes 0, yes or no?
Yes.
This element also becomes 0. And the lower diagonal anyways is 0. So do you see that every operation you are going to get 1 1 0 extra, and at the end of the day you will get a diagonal full of zeros, which means you would only, what does it mean? Only all the eigenvalues are 0, which means your product is going to be 0. This matrix itself will go to 0. Just go and like check it for every ij. It will be very simple. I don't think there's any problem with this. That's why it satisfies this equation. Just I think calculations are not a good thing to do in class. I'll not do it. Okay. So now let's see an example. That's the best thing to motivate. say you have a matrix A. 1, 0, 0, 1 and 1. This is your matrix. Right? If this is your matrix, my question to you is, what are the eigenvectors of this matrix? What are the corresponding eigenvalues? How will I do it? What should I do if I have to find the eigenvalues? And don't worry about the Hermitian matrices. We will see them. Find the eigenvalues. What will I do?
We'll find the characteristic equation, solve it and find.
So characteristics equation is what? Here?
Lambda square minus 1 equal to 0.
Everyone following? T square minus 1 equal to 0. So T is equal to, what is it? Plus minus 1, right?
Plus minus 1, yes.
This would have two equations. Let me just what should I do? Which one should I? Take? This is too much. This is what we'll do. For this, what are the equations? T minus 1, 0. Let's do this for this matrix. Just exactly. Yeah, we can do it for this matrix. So what are this characteristic equation? This is T square equal to 0, right? Or just T square, right? This is the characteristics equation. That's determinant of Ti minus A. That is T 1, 0, T. Agreed? So what is the determinant value? T square, right?
Yes.
So
Yes.
T is 0. 0, 0. Both are 0. So I should have ideally two vectors corresponding to the 0, right? In this case, corresponding to 0 eigenvalues. So my equation Ax is equal to lambda x should have two equations. Ideally, because you have two eigenvalues, two t's, right? Lambda 1 and lambda 2. Yes or no? Both are 0. This should ideally happen, right?
Yes.
I should have two equations that solves it. But you see in this case, how many? So what is the dimension of the null space over here? What is the dimension of null? 2. First, this you come here, then what do you do? Pivot, you move right. If everything below it is 0. How can it be 2? What is the dimension
Yes,
of the
it's
column? 1. You have a non-zero column vector. So anything in 1, 0 will be, but you see, the dimension of null space is 1. So you only have this equation, A 1, 0 is equal to 0. Correct? So this is also called a, so you see you have a, what is the algebraic multiplicity of 2? Algebraic multiplicity of 0? What is the algebraic multiplicity?
It's 2.
But what is the geometric multiplicity? The determinant of or the dimension of the null space of A minus 0i. What is this dimensionality?
It is
1.
equal to 1.
So we are observing one thing. Generally, it will not happen like this. For example, if you are given a matrix A equal to 2, 3, and say 3, if this is your matrix. So what are the eigenvalues here? You're told to find what are the eigenvalues?
2, 3, and 3.
Example.
Those will be.
Okay, so you will have t minus 2, t minus 3 squared. Yes or no?
Yes.
So t 2 comma 3. What is the multiplicity of 2? Algebraic multiplicity?
1.
1. And geometric multiplicity we'll see. Give me some time. And what is the algebraic multiplicity of 3?
2.
Now what if I'm told to find the geometric multiplicity of 2, what will I do? What do we have to find? Dimension of null space of A minus 2i, right? Yes or no? How many null space vectors do A minus 2i have? Correct?
Yes.
একটা second. Dimension of null space. ঠিক.
So this is 0, 3, 3, 0, 0, 0. What is the eigenvalue for this? What is the eigenspace vector for this?
It will be 1, 1, na?
1, 0, 0, right? 1, 1, 1. 1, 1, 1 will
Means
also do.
in diagonal 0, 1, 1. I'm telling.
That is true. True. I was asking what is the dimension of this matrix?
Dimension is 3.
Dimension of the null space.
Dimension of the null space is 2.
Which is
2.
1 it will be.
No, 1, 1, 1. 1. Sorry. 1. 1, sorry.
So this is clearly you can see 0, 0, 0, 0, 1, 0, 0, 0, 1, which is the dependent rows. These are the independent, right? Independent, this is dependent. This is your F. So just put 1 in the dependent place and zeros in the independent. This will give you 0, 0, 0. Yes or no? If you just multiply 1, 0, 0 to this, do you get 2 into 1, 0, 0? I am doing Ax is equal to lambda x here and finding dimension of null space vector here. Null space of A minus 2i. Do you understand that 1, 0, 0 is the dimension in the null space of A minus 2i?
Please repeat.
What is the geometric
একটা
multiplicity?
মইনাকদা,
What is geometry? Don't stop me. What is geometric multiplicity? First tell me this. What is the definition of geometric multiplicity I just told a little while back? Just now I told, I've written also, it's written here.
Well, like the dimension of A minus lambda I for that lambda. For that T.
Dimension of null space.
Null space.
What are we solving? A minus lambda I x is equal to 0, right?
Yes.
And we saw that we have, say if you have two such cases for which lambda has repeated roots, we are trying to see if x also has different vectors or not. In this case, we are not having. So what is the dimension of the null space? You already told me it's 1, right? Correct?
Yes.
This is the column space is 2. and the dimension of the null space is 1. Do you agree that if I multiply 1, 0, 0 with this matrix A minus 2i into 1, 0, 0, it is 0? Yes or no? If I'm told, if
Yes.
you are told to find the eigenvector, you can find it this way. So what does it mean? That 1, 0, 0 is the eigenvector, right? Corresponding to 2.
Yes.
So repeat means 2, 3, 3, 0, 0, 0, 0, 0. What would happen if I multiply 1, 0, 0 to this? I'll get
Like 2 times 1, 0, 0.
2, 0, 0. This is what you're telling me to repeat. Now tell me what I have to repeat. So this is
Yes, I have
lambda.
understood.
This is your x. Now Partho, tell me what is the question.
ওই যে a minus 2 এর নাল স্পেসটা তো বেসিক্যালি ফর্মালি হবে k সাম k into 100, তাই তো?
Yes.
হ্যাঁ,
But we will
x1
only
টাকে
take.
ফ্রি ভেরিয়েবল নেব।
Yes. The way we did it, that will be the free variable. Similarly, now if I remove 3, a minus 3i, what will happen?
তো -1 0 0 0 0 0 0 0 0
Minus 1, 0, 0, everything is 0. Right? Now, what is the rank of this matrix? Or dimension of the
rank dimension
null
of
space is
null space is 2.
yes. We'll see these. This is in the previous case. This is called a degenerate matrix. We'll see why is it bad. Degenerate matrix. If your algebraic multiplicity is greater than geometric multiplicity, it is called a degenerate matrix. We'll see why is it bad for application purposes. In this case, algebraic multiplicity is equal to geometric multiplicity always for all lambda. Now we'll see why. So now if I ask you what are the eigenvectors of corresponding to 3, Uthrij? What are the eigenvectors corresponding to 3?
Like we can have 0, 1, 0 and 0,
Good.
0, 1.
0, 0, 1. So these two are the eigenvectors corresponding to 3. This gives you an idea of geometric and algebraic multiplicity. Does it give you an idea? It gives you a broader idea saying when you have k lambdas, you can have at most. So this is an intuition for, we'll show it formally also. Algebraic multiplicity has to be greater than equal to geometric multiplicity. That is for there to be a lambda, ax equal to lambda x must hold. This must be may be repeated, but x may k times. X may not have k independent vectors. Okay, that is corresponding to that is the null, that is dimension of what, in other words, dimension of null space of a minus lambda I will be less than equal to, will be greater than equal to 0, or the dimension of a minus column space of a minus lambda I will be, what will it be? What? Just the intuition is, so if you have k repeated vectors, k repeated eigenvalues, the x may not be repeated n times. The x may not have independent vectors. So what will happen if it does not have independent vectors? The dimension of the null space will be at least 1. It must have. The dimension of the null space will be Between 0 and k, yes or no? Just now 1 and k, just now as we saw in the first equation.
Yes.
We'll see why it is true. At max, it can have k solutions because a1, ax1 equal to lambda x1, ax2 equal to lambda x2, dot dot dot, axk is equal to lambda xk. At max, it can have this. It can also have less. Minimum, it has to have 1. Otherwise, there is no meaning of the solution of lambda, right? It must have 1 because then only why does at least it has to be 1? Because a minus lambda I has to have a solution, yes or no? A minus lambda I has to have a solution.
Yes.
So if that has to have a solution, at least one x must exist to in null space of a minus lambda I. But this is just the intuition that I'm trying to build. I'll like clearly we'll see in some time. So what have we learned till now? We have learned, give me 15 minutes and I'll just build up the theoretical properties also. And then it will be simpler for you to understand. Let us do some easy questions first, and then we'll go to other tougher questions. So we learned what is algebraic multiplicity. We learned what is geometric multiplicity and how we can find the eigenvalues and eigenvectors of a matrix, right? Good. So let us do one question, easy question first. The properties of eigenvalues. So if determinant of A is 0, then show that the rank is less than n and there is at least one eigenvalue which is equal to 0. How can I show?
Yeah, so it means that rank is less than n mane ki mane rank is equal to n minus the dimension of null space. So dimension of null space টা যদি greater than 0 হয় তখনই সেটা র্যাঙ্কটা হবে less than n. তো মানে so there must exist an eigenvalue or a lambda term, at least one in it.
What is eigenvalue? Eigenvalue.
Now
Okay.
t term.
Yeah. The eigenvalue will be so the dimension of null space of A is greater than 0 because otherwise determinant cannot be 0. Do you agree? Is it okay? So do you see rank is less than equal to less than n? Yes or no?
Yes.
So now you have to show that at least one lambda is equal to 0. How can you show that?
Means there is at least a solution in null space. So,
No. So do you know? Remember the property product of the lambdas? That way also you can say. I think I'll check that. But you're saying there is at least one solution for ax equal to lambda x, right? 0. So that has to have at least one solution for this. At least one solution. True, but it does not give you the idea that this using this thing. Do you agree the product of the eigenvalues have to be determinant of A?
yes.
So if this is 0, at least one lambda I equal to 0. Agreed?
Yes.
Okay. So we'll take 15 minutes more and I'll complete up to SVD today. Yes, and then next day we'll start with machine learning. Let me see how much we can do. Let's not rush it. Let's do number 3 now. I think it will be done now. We are there in that zone. So A plus lambda I has an eigenvalue of lambda plus lambda I plus alpha. So how can I prove this? Number 3.
আচ্ছা মইনাকদা ওটা
A
কি
plus
for all i হবে কোয়েশ্চেনটা for all x for all i হবে কি
for all I, x and x also. for all lambda comma x pairs, eigenpairs. Okay.
Yes. Okay.
Ball. Osmith ball. This is a simple question. That's why I'm asking you. If you have been following what we are doing, at least definition, you should be able to tell. Okay, you're not replying. Good. Uthrij? Ball.
We are talking about question 3, right?
Yeah. So A plus alpha I is a new matrix. I am saying the say for A lambda comma x is an eigenpair. Then we have to show that for A plus lambda I plus alpha comma x is an eigenpair. How will I show this? So what is the definition? Ax is equal to lambda x
Lambda
is
x.
given to me.
Yes.
What can I write? Alpha I x is equal to alpha x. Can I write?
Yes.
I into x is x. X
Yes.
is a
Yes.
vector.
Yes.
I is identity matrix. Now I add these two. So A plus alpha I into x is equal to alpha plus. Done. Clear to everybody? So for this matrix, again, this you have the same eigenvector and this is the eigenvalue. Clear to everyone?
Yes. Acha,
Now,
Mohinanda. I have to ask a thing. Do A and A transpose always have the same eigenvalues?
I don't like A transpose. Why will it have different eigenvalues? I don't
Yes.
understand. Like determinant of Ti minus A. This is a lame question, man. Determinant of yes or no?
Yes. Break it up over the sum. Ti minus A transpose, huh?
So it will have same eigenvalues or not?
Yes. আচ্ছা আরেকটা জিনিস হয় না তা if two matrices have the same characteristic equation, can I say that the matrices are same?
Matrices are
Same.
no.
আচ্ছা, fine.
Only the eigenvalues are different. I'll give you. This is here only. I can give you an example. This is an example.
Which one?
With this, you can make an example yourself. 0 1 0 1 0 0.
Oh, acha. Yes.
And you can make many more complicated examples. It just means their eigenvalues are same. The energy in them is same.
বুঝতে পেরেছি।
The eigen product of the eigenvalues gives you sort of the amount of. So that's why it's called a characteristic equation, because characteristic equation has all those information. So now we are trying to understand one thing, that is we'll see this in the next section. We'll be seeing something called as a similarity transformation and see why it is useful. Okay, so I'll just with this I will, where is it? I don't really see, but let's check. So A and B are said to be similar matrices. That is, you can represent A and B as similar matrices if you can write A as S inverse BS. And why is it you may ask me, why is this anyways relevant to what we are doing? And I would be totally agreeing with you. But there is a definite advantage of using this equation. So is the definition clear of similarity matrix? If you can use the same matrix to multiply and take the inverse of the matrix and multiply it to the left, the row space and the column space, the matrix, you get it from the, you get back the matrix. Two matrices are said to be similar. I'll show you some examples. It will become very simple. So one trivial example is the identity matrix. It's similar to itself, right? Where S can be an identity. Agreed? So we'll see other examples very soon. But is this equation clear to you? So let me just write it. And I'll also do this diagonalizability. And then I'll come back over here. Okay, let's try and do this. I'll do it at the end. So the question is similarity transformations. It is A equal to S inverse BS, or A equal to S B S inverse. Both are equivalent, homologous. Then they are said to be similar matrices, right? And why are they said to be similar matrices? We'll see. Then A is similar to B. Okay, they are said to be similar because similar as they have the same characteristic equation. So the same. So you're asking me the question: do they have the same characteristic equation? Matlab same eigen, same matrices. Can you see a matrix which is not? Same characteristic equation means they are similar matrices that you can always write them as this transformation. Is it clear, Partho? Am I audible though? We'll see why it is the case, but is the statement clear? A and B have the same characteristic equation. B, let me write it mathematically. Is this okay?
Yes.
Yes.
Okay, how do I prove this? PA of T. Let me, if I write, I can write this as O3. Tell me what can I write this as?
A minus lambda, I guess, Ti minus A.
So what can I write this as? Now I want to express it in terms of B. What will I do?
Ti minus SBS inverse.
Ti minus S inverse
SBS
BS or
inverse.
whatever. Both.
আচ্ছা
Okay.
আইটাকে আমি কি লিখবো T into SS inverse.
S inverse S. Okay. Now tell me O3's next step. Partha told me this step. Next step.
Like we can take common S inverse and det A into
This is what you mean?
Yes.
What is determinant of product of matrices?
Product of determinant. মানে যদি সবকটা স্কয়ার
So
ম্যাট্রিক্স
it will
হয়
become
then on.
I.
Of course, if they are square matrices, all are square matrices. Right?
Yes.
This is an identity. And we know determinant of S inverse S is equal to determinant of identity, which is equal to 1. So therefore, determinant of S inverse is equal to 1 by determinant of S. Yes or no?
Yes.
Yes.
So this is PB of t. So this helps me doing all my questions simply, because now if I can write, if I know a simpler transformation from A to B, if I know a transformation from A to B, and B is some diagonal matrix or any matrix, if B is some diagonal matrix d1, d2, dot, 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 dn, right? So I can directly tell eigenvalues of A is same as d1, d2, dn, right? This is one of the applications of similarity transformation, right? Is this clear? So if B is diagonal in some way, then A will have the same eigenvalues as the diagonal elements. Do you agree?
Yes.
Yes. Yes. Yes.
So that's what is used in diagonalization. We'll see what is diagonalization now. We'll see a couple of more things, and I'll not burden with you with SVD today. There are two interesting things we'll be doing next day. So let us see what is diagonalization. So say we have algebraic multiplicity is equal to geometric multiplicity for all lambda i's. Okay. Even if they're repeated, they have independent null space vectors. Is it clear? You now know what is algebraic multiplicity and geometric multiplicity mean, and what is equal to having them equal. That's why I spent so much time on each of these. I can just write now. Can I write ax1 is equal to lambda 1 x1 and not care about the values of lambda 1s and lambda 2s and so on? Lambda i's can be repeated now without worrying, right? Because I have different x's, yes or no? X's are different as
Yes.
xi's are different by independent, to be exact. So I will have a2 as a into x2 is equal to lambda 2 x2. Can I write an? I will have n roots, so I will have n equations, yes or no? Yes or no? For n eigen equations. Agreed?
Yes.
What can I write this as? Can I write this as x1, x2, xn? Then what will it be? Lambda 1 x1, lambda 2 x2, dot, 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 lambda n xn. Right?
Yes.
Is it okay? Corresponding to each of the xi's, I'm doing the same column vector multiplication. Yes or no? Combination of columns, O3 is okay?
Yes.
Not okay? Let me write this as S.
No. Yes. Yes. Okay.
So can I write this as x1, x2, dot, 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 xn? And what can I write this as? Lambda 1, lambda 2, lambda n, yes or no?
Yes, definitely.
This lambda 1 will be multiplied with this, again row element, these are all zeros.
Yes.
Is it okay, others?
Yes. Okay.
So now what do you see? As is equal to S, this lambda matrix. This is also called lambda 1, lambda 2, all the diagonals, right? These are your eigenvectors, eigenvalues. eigenvalue matrix. Okay with it? So A is S lambda S inverse. So you see A is similar to lambda. Yes or no? Right?
Yes.
So if you did not have AM equal to GM, what would happen? Say you had lambda 1 is AM equal to 3 and GM equal to only 2. What would have happened?
Like all xi's would not exist, so we wouldn't
Good.
have written the S matrix.
So this x's x S would not be independent, right? S would not be invertible, right?
কেন বললে গো মৈনাকদা এই জায়গাটা ক্লিয়ার হলো না?
If there are not n independent vectors, how can S be independent?
ও আচ্ছা, মানে S টার ডিটারমিনেন্টটা 0 হবে then.
Yes, so you cannot take
Hence
inverse.
না,
So
সিঙ্গুলার.
so you cannot take inverse. That's what I'm saying. Yes, singular.
Yes.
Okay, now I am being burdening you with this idea that arithmetic mean is always greater than geometric mean. I'll show you a simple proof with this similarity. Show that geometric mean is less than equal to arithmetic mean. Okay, I'm giving you a hint. I will be using the same method that I used here. Can you tell me what steps should I do if I give you this hint? So say geometric multiplicity is equal to k. What does it mean?
There are k
for lambda
dependent columns.
Let's see. For lambda geometric multiplicity equal to k. What does this mean? Definition Otrich. What does this mean?
Like dimension of null space of A minus
lambda I is equal to k.
Yes, K.
Which means there are k independent vectors in null space of lambda. Do you agree?
Yes.
Good. If you agree, so can I write ax1 equal to lambda x1, ax2 is equal to, and let us note them as x1, x2 dot xk. Happy? Okay.
Yes.
So lambda x2, and I write it k times axk lambda xk. Okay. I can write this. Yes or no?
Yes, yes.
So now you tell me, can I write also this? x1, x2 dot xk. I can write this. And from xk plus 1 dot xn generated by Gram-Schmidt. Gram-Schmidt to null space to the Gram-Schmidt perpendicular to null space of A. Then they are not in null space. Do you agree? Right?
Yes, sort of out of space. Huh?
So they will never be equal to 0 then. So this matrix will become invertible now. Do you agree? They are independent, and they are mutually independent. This is in the column space. This is in column space. This is in the null space. You can also make this in the row space. Same thing. They're perpendicular, right? Yes or no? Because they're n-dimensional.
Row space হলে তো ওটা হয়ে যাবে null space of A transpose, না?
No, this is null space of A. I have found out this is for the eigenspace of null space of A minus lambda I. This k vectors. I am going to generate rest of the vectors perpendicular to these k vectors. That's what I mean. Null space of A minus lambda I. So the row space of A minus lambda I, not exactly A. Clear?
Yes.
Clear every others? Clear?
Yes.
Why is it? Is my screen visible, not visible?
No.
Okay, I'll share again. Okay. I think it's visible now, right? You can see
Yes.
my screen? Good. So now what can I write? Can I write this as lambda 1 x1 lambda or lambda x1 lambda x2 dot 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 lambda xn and some matrix. Let us write this as Q matrix, not Q M matrix. Doesn't matter. Is this okay?
Dada, that should
these,
be up to lambda xk.
yes. Sorry. So this is your n cross k, and this M is how many dimensional? N minus k cross this, right? N cross n minus k. No doubt.
Yes.
Now I can also write this as this way. Can I write? I will write here as x1, x2 dot 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 xk. Again, I will write xk plus 1, xk plus 2 dot 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 xk or xn. So let me just take a little lesser space over here. Just too much space. Okay, dot 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 xk, and you have xk plus 1 dot 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 xn. Okay. Now, do you agree? This is equal to lambda into ik. You will have, that is, let me just write it for you. K lambdas here. Yes or no? This is ik into lambda. Do you agree? For these columns?
Yes.
And I'll put a zero below. Then I'll get back these columns as it is. Yes or no? If you have any questions, please ask. Yes or no? First, lambda 0 0 into this is equal to lambda x1.
মানে x1 থেকে xk অবধি সব করে ল্যামডার সাথে মাল্টিপ্লাই হচ্ছে।
Exactly. And the rest of it, I can just.
And the rest is being cancelled out, I guess.
Rest doesn't matter. Not cancelled out. Rest can be any matrix which has to be found by calculation though. But let me write this as design matrix 1 and design matrix 2, such that these two product is equal to M. Right? I can always make design matrices so that it can happen. They will always have a solution. There's less number of unknowns and less number of equations and more number of unknowns, you will be able to solve it. Is this clear? So this is just breaking this into two parts, nothing else. This first k columns is clear, right? For the
Yes.
first. Hello, am I audible?
Yes, now.
Yeah, now I can hear you. Go on.
No, now I can hear. So I couldn't hear you
Okay.
previous.
Okay. So did you understand that if I write this as some x tilde matrix, so my D matrix x tilde D is equal to M. This is what I claim. This is how you will solve it and find D. You happy with my arguments?
Yes.
So now can I write A? So this is a matrix S is equal to S Ik D1 D2 0. What do I get? Is it a similar matrix? This matrix and A is similar, right? Agreed?
Yes.
Yes.
If they are similar, what will happen? The characteristics of A will be T minus lambda to the power K into determinant of D2. Do you agree?
Yes. Yes. Yes.
Uthrij, এটা determinant কি হবে? Block diagonals. This is why I was teaching block diagonal matrices. So this you can take the determinant of this into the determinant of this if you expand with respect to these two diagonals. Yes or no? These are
Yes.
all determinants are recursive in nature. That's why this block diagonal partition matrices are. So did you understand? So the PT will be is equal to determinant of Ti minus. Now বুঝতে পারলে ask me, okay? I'm waiting for this and then it will be done. This is the last part. Any question? So now what can you tell? So how many roots does lambda have? How many repeated root at least? So arithmetic multiplicity, algebraic multiplicity of lambda is at least k. Yes or no? From here also I can get lambda. Here also I can get lambda, right?
Acha, yes.
So at least k will happen. So you can prove algebraic multiplicity of lambda is greater than or equal to geometric multiplicity of lambda. Clear to everyone? So this is, I'll give you a homework, you solve this and then you'll understand very, very well. Question 1 is diagonalize A equal to the, we had done some matrices before, right? Where is it? The first class matrix should be, let me just check. Should be a 3 by 3 matrix, simple one. This 4 by 4 is too big for you. So this you can do. So if you are told to diagonalize this thing, you diagonalize this. Diagonalize this. And now my second question is, this is 1. And the number 2 question, please solve it. And unless you do it, you'll not get the, you may understand the theory now, but by hand also you'll have to solve. This will give you, so what are the 2 things you'll have to do? Can you tell me by the time I write the second question? When you are trying to diagonalize this? I'm waiting.
Like find S.
Yes, you have to find. How will you find? That's what I'm saying. The steps.
Is the first we'll find the eigen vectors of A, place them
First, you
as
will find the
rows
eigenvectors.
of S.
Like eigenvectors will come from heavens.
First we'll find the eigenvalues.
Okay.
And then we'll find the eigenvectors.
There is nothing called eigenvectors when you're finding it. When you're finding it, you will find the vectors of the null space of A minus the eigenvalue.
Yes.
Okay. Try to diagonalize this. And A3 would be try to diagonalize this. And tell me which of diagonalize if possible is the question. Okay. So before we end, so let me see where you have we covered all of it? We have covered AM greater than equal to GM, right? AM greater than equal to GM covered, diagonalizability covered. So what is the criteria for diagonalizability? Criteria is, we just proved it. Utrich, what is the criteria?
Like AM equals to GM.
For all lambdas, right?
Yes.
Yes or no?
Yes.
Or if all eigenvalues are distinct. Which also implies, or this implies this. Can you tell me why? If all eigenvalues are distinct, AM equal to GM?
Yeah, then every AM has, for everyone, AM is 1.
Yes. And GM at least has to be 1, right?
GM at least has to be 1, so it is 1, 1.
So we proved GM is less than, this is the definition we proved. So if all are unique, then for this, all lambda AM of lambda is equal to 1. Therefore, GM is equal to 1. Therefore, diagonalize. Good. This question let us will do, and then so we have shown this as well. Now show that if two matrices commute if they are simultaneously diagonalizable. Can you tell me how to do this? Simultaneously diagonalizable means the same S or the same design matrix S diagonalizes both of them. And this will tell you that they commute. Can you tell me? So I have 3 more questions left. Will hardly take 6 minutes and we will stop. Very short questions. Number 4. It is told A is equal to S inverse lambda 1S. B is equal to S inverse lambda 2S. They are simultaneously diagonalizable. Right? Did you understand the question? Is this clear? This is a theorem which says that AB equal to BA if and only if they are simultaneously diagonalizable. This is a theorem. We will not prove the other side, that is a design choice.
বলবো কি করে হবে না তাই
No, I'm saying, so I will be saying, I'll be proving only one direction. The other direction will not be is only like making the matrices. You can look it up on the internet. I'll be proving this direction, but remember, this is a very, very important, again, another case where you're using similarity transformation. So same eigenvectors are being used. For A and B. So they have same eigenvectors, have same E vectors. Okay, but no, not same eigenvalues. Okay, so if this is the case, I am going to prove if simultaneously diagonalizable means AB equal to BA. The reverse is technical. I will share it with you in the group, but I'll not do it in the class. There's not much time there. This is technical, but let's do the easier one. So what will I do? Tell Partho, tell me.
So AP হলে কি হবে, মানে এটা S inverse lambda 1 S inverse lambda 2s
Good.
হ্যাঁ ওই S আর S inverse মাঝখানেরটা হয়ে যাবে I S inverse lambda 1 lambda 2s
Okay,
lambda 2
and BA
এবার
is
BA হচ্ছে S inverse lambda 2 lambda 1s
everybody clear? Otrich clear?
Yes.
So this is equal to S inverse lambda 2 lambda 1 S. If it is clear now, tell me why they are equal now. You have told me. Now Otrich will tell me now. You have already told me the answer. Otrich, tell me if you are following.
Means I was trying to figure out that only, because means why that delta 1 delta 2 equals to delta 2 delta 1. But
Well, they are diagonal matrices now.
Oh, acha, yes.
They are diagonal matrices. Lambda 1 lambda 2 is equal to lambda 2 lambda 1. Hence true, hence proved. Good. Last question. Show that if T is a polynomial and then P of lambda comma x is an eigenpair for P of A. How will I show? So this one I'll just give you as a homework, and this is very simple. Please do this as a homework and I will discuss. If not, I'll just write please discuss, please do this as a homework. You understood the question, right? The question is,
ও মানে এখানে কি a minus p lambda I করে করতে হবে?
no, I'm showing this. You have a general polynomial, okay? The general polynomial, which is a naught t to the ai t to the power I equal to 1 to n. Okay? Clear question? Let me write P to be clear. This is the polynomial P general. Okay. Now my question is, PA general has P lambda comma x as the eigenpair. Is the question clear? What is PA? It is a matrix, right? Is it a matrix or not?
Yes.
Is the what is it? AI? A to the power I? I'm doing it anyways. Leave it. You will not do, I know. So let me only do. Is this okay?
Yes.
So now x is an eigenvalue, then ax is equal to lambda x. Yes or no? This I want you to have this practice. That's why I'm telling. X equal to lambda x if x is an eigenvector. Yes or no?
Yes.
So if I multiply x on both sides, what will happen? I'll get PA of x as AI.
আচ্ছা ওই যে AI into x টা না ওটা একটা iterative multiplication হয়ে যাবে।
So
ax হবে lambda
O3 tell me what will what O3 will tell me now. You have understood. O3 tell me what is a to the power ix, and we'll see this application next day.
Okay, lambda power I
In
into
Fibonacci
x.
series. Only 2 things are left, like 30 minutes.
Lambda power I into x.
Good. I to the power I minus 1 into lambda x. By recursively, it will be lambda to the power I x. So what is this going to be? AI lambda to the power I summation I equal to 1 to n into x, correct? Which is P of lambda into x. Yes or no?
Yes.
That's it. Okay, we'll stop with the last thing, that is show that if two matrices are symmetric, they will have real eigenvalues, and the eigenvectors will be orthogonal or unitary. The question is, this is the one of the questions that people ask me also. So if A Hermitian is equal to A, or A transpose is equal to A, show that they have real roots. See, Hermitian transpose does not make it interesting. Do you see that A transpose is same as A Hermitian for a real A Hermitian is same as A transpose for real matrices?
If Im equals to 0, huh?
For real matrices, it is true. Okay, if they are real, if such they have real eigenvalues, how do I prove it? Their eigenvalues are real. So where do I start?
So characteristic equation ta theke can't I show if it is
No.
quadratic?
I can show quadratic.
তাহলে
It can
t
be
square
n by
minus
n,
4ac.
we can show that, but it will be it will not be a quadratic, na? It will be a n-ordered polynomial.
N by n, is there any way like quadratic to show for real roots?
No, more than 5, there is no general formula. So Utrish, can you give me an idea how to start? If there is an eigenvalue eigenvector solution, just where do you start? Blindly start from one thing. I'm telling you that.
Like means I was thinking of the construction of AH. So if we have AH minus A, then we have all the diagonal elements cancelled.
But that is much more cumbersome. But whenever I am thinking about real values, I may try it, but I don't have so much time to try it now. But there's a very simple way you can do it, like from the definition. Can you tell me? Like, see this and tell me. See this equation. Like, this is the eigenvalue equation that I wrote for A. Do you agree? Yes or no? This I have to show this is real, right? This is what I have to show. Am I audible?
Yes.
Okay,
না,
so then if I
real
take,
আর কোন property আছে ওটাই I am thinking যে how to.
I'll take sec Hermitian. You have given this, na? You have been given this. Use this. When will you use this? Take Hermitian on both sides. What will you get? Yes or no?
Yep.
Okay, is it clear? Hermitian matlab we already discussed. A Hermitian is A transpose conjugate.
Oh, lambda equals to lambda conjugate.
You told. Now what is this? This is A. Yes or no? From the definition of Hermitian matrices are symmetric matrices.
Yes.
So X Hermitian A is equal to lambda Hermitian X Hermitian. Yes or no? True. From symmetric by Hermitian. আরে Hermitian এর প্রবলেম হলে এটা হচ্ছে Hermitian matrix A plus IB. What if diagonals cannot for Hermitian matrices diagonal has to be always real, right? You know that, right? Why do diagonal has to be real?
কারণ যখন আমি এ হার্মিশিয়ানটা নেব, আফটার আই transpose, all the diagonal elements should be equal to their conjugate. So for it to be equal, yes.
So this is equal to AII conjugate. Right? AII conjugate has to be same, right? With AII. Yes or no? A Hermitian II has to be equal to this is, do you agree? Yes or no?
Yes, yes.
And that has to be equal to AII. Yes or no? If it has to be equal, they have to be equal, right? For symmetric matrices, which means equal to AII. So AII conjugate is equal to AII. Yes or no? So diagonal has to be real, right? এটাই ভাবছিলিস,
yes.
এটাই তুই ভাবছিলিস।
না না, ঠিক এটা নয়, বাট এটা বুঝতে পেরেছি।
এবার বল এটাকে আমি x, যদি দুদিকে x দিয়ে মাল্টিপ্লাই করি কি হবে? এটা কি হয়ে যাবে? Yes or no?
Yes.
What is x transpose x? এই জন্যই হার্মিশিয়ান নেওয়া হয়। এবার তো এটার জন্যই আমি ওয়েট করছিলাম। I was waiting for this to show to you. So lambda equal to lambda transpose, lambda conjugate. So one example is a plus ib, c plus id. If you have to find the radius of this vector, what is the radius of this vector? It is a square plus b square plus c square plus d square, right? If you have to find the norm of this vector that we discussed last time. If this is x, this should be the definition of, should be definition, yes or no?
Yes, yes.
Since all are, what is the radius of a real what is the radius of us? I'll give you this example. So you have a complex number. Complex numbers are also vectors, right? They're the two numbers stacked to one another, yes or no? This is essentially writing a b c d in a matrix instead of writing two. Complex numbers are essentially that, right? They're also like a
Yes.
plus ib, two independent, they're like vectors in argand plane, x and y. You studied in 11 and 12. So if you had to find the radius of q, what did you do? You did q star into q, right? q star into q করতিস তো, a minus ib into a plus ib.
Yes, yes.
q star হচ্ছে কনজুগেট, যদি গুলিয়ে ফেলি দুটোই সেম। a square plus b square করতিস, সেই জন্য we don't just take x transpose, we take x Hermitian in complex matrices. বুঝতে পেরেছিস? যাতে কনজুগেটটাও হয়ে যায় আর রিয়েল পার্ট, শুধু রিয়েল পার্টটা পড়ে থাকে। ক্লিয়ার?
Oh yes, understood.
এটাকে দেখ, এটাকে x হার্মিশিয়ান যখন আমি করে দেবো, এটা কি হয়ে যাবে? এটাকে এরকম ভাবে লেখা উচিত ছিল আমার, c plus id। যখন x হার্মিশিয়ান করে দেবো কি হয়ে যাবে? a minus ib c minus id, এটা হয়ে যাবে। এবার মাল্টিপ্লাই কর, এবার দুটোকে মাল্টিপ্লাই কর, x হার্মিশিয়ান x, পাচ্ছিস কি পাচ্ছিস না এটা? You're getting right?
Yes.
So done. So real it is proved, and they are orthogonal. How will you prove? So since they are real, say this is the diagonalizability matrix, so they have to be equal to a Hermitian, S inverse Hermitian, lambda Hermitian, S Hermitian. এখান থেকে কি করে বলতে পারবো? How will I say that from these two equations that the S must be orthogonal?
মাল্টিপ্লাই করে দেবো ওই a ইন্টু a হার্মিশিয়ানটা করে, ওদিকে আসবে i আর আর এদিকে আসবে s
No
ইন্টু
রে, I compare these two equations, these two, lambda Hermitian is equal to lambda, right? We have proved just now. Since
Yes.
they are real. Yes or no? So S inverse Hermitian. Yes or no? This has to be equal to A. S Hermitian is equal to S inverse Hermitian. Compare both sides. What will you get? S inverse is equal to S Hermitian. What does it mean? S is ortho or unitary. That is, A has orthonormal vectors. Yes or no? A has orthonormal vectors. With this, I'll stop today. Any questions that you need to think that should be added to this discussion, or I'll stop recording and then I'll take the final discussion. Okay, we'll stop here. Next day we'll do what is called singular value decomposition. That will take 15 minutes. And I'll do a special question called Fibonacci series, which I didn't do properly last time. I'll do it this time. This should be done within half an hour, and then we can go into like rest of the 1.5 hours. We'll be doing machine learning. We'll be doing linear regression next class. Okay, with this, I'll stop recording.